following axes. The first is whether we have multidimensional continuous variables versus one-dimensional discrete. And the second is whether we have multi-valued variables versus single-valued. So the thing to notice over here is that as we move across these representations, across the direction of the arrows, there is always information loss. So in order to go from the stochastic layer to choosing a single continuous value, you need to basically discard a lot of information. The same way when we project from the stochastic layer to the categorical layer. The same way when we go from the categorical to a single sort of category. Also notice that between these two worlds, between signals and symbols, there is a need for some sort of a classifier that takes the probability mass that belongs over here and spreads it over the categories. Now, let's see how the three layers work in actual operation within the system. Let's describe the processes. First of all, suppose that we have incoming sensor information. This is basically fed to the stochastic layer, first of all. Let me give you an overview. In general, when we're going to have sensory stuff, they're going to connect to the stochastic layer. Whenever we're going to have linguistic stuff, it's going to connect to the categorical layer. And the three layers are going to basically be updated in order to conform to each other. So we have an update to the stochastic layer. Then we actually choose a single value from there for the continuous layer. And then there is this projection process that projects the stochastic to the categorical on the basis of trained classifiers for the categories. Now, if we look away for a while and we don't have sensory evidence anymore about the position of the object, then we basically have to increase our uncertainty about the object, and we can empirically find out how much we have to do that. So there's a diffusion process that takes over that increases the uncertainty about the object in the stochastic layer, and again we project to continuous and categorical. So this is after 10 seconds, say, this is after 3 minutes, say, where we're not sure about where it is anymore almost at all. If you project down to the categorical layer, you're going to see that now we're starting to get spread across different categories. And the equivalent verbalization is at the center for the case of certainty, most probably at the center when we have this little spread over here, and all the way to I have no idea when basically we almost get a sort of uniform distribution. Finally, the case where we don't have sensor information coming in, but we have linguistic information coming in. In that case, we're not feeding the stochastic layer, but we're feeding the categorical layer. Take two examples. Imagine a red ball at the center. This projects to probability 1 for the center category, versus imagine a red ball, which projects to a uniform sort of distribution across the categories. Then we have to unproject, basically do a backwards unprojection from here to the stochastic layer. And what we basically do is that we get the receptive field of the classifier and we spread the probability across the receptive field of the classifier for this category. The same thing happens over here and we get this uniform distribution. Again, this is only one possibility. In the thesis, there's a description of many other ways of doing the same thing. The essence of the problem is how do you go from here to there and how do you go from there to here? And there are many ways to do that given different assumptions, as you're going to see. So if we had, for example, better priors, we could actually go and not spread uniformly, but spread on the basis of a prior about our knowledge about this category. Apart from that, there's a need for a matching algorithm. So whenever we see an object or we get sensory evidence for something, if we had prior sensory expectations, we need to match the sensory expectations to the sensory evidence. And there can be three outcomes of this match. We can either create a new object, or update an existing object, or destroy an object. And there are also cases where we basically destroy an existing object and create a new in its position. So say that we're looking at a part of the table, and this is what we get through vision, and this is what we have right now. We look away, then suddenly one of the objects is missing. The matching algorithm tries to basically match the sensory expectation to the incoming stuff. Because it's missing, we have to destroy the object. Then, when we see a new object, we have to create one. The thing to notice over here is that the sort of the matching metric is basically like a multidimensional distance function across the properties of the object. So we need something that's going to be pretty much the same position, pretty much the same size, pretty much the same color, and so on. Example contents of the GSM. I will not get into much more detail. So this is a specific time instant. There's a description of the self, of the agent of the self, a description of the user, a description of the objects. The description of the self breaks down to the body, the interface, and the mental. So this gives us the capability of actually entertaining two things. You can have the beliefs of the robot and also the embedded GSM of the robot itself. So you can have differences between what the robot believes and what the robot believes he believes. So if you want to find a way to represent partial conscious penetrability, you can do it by having a difference between this thing and the estimated GSM of the robot. You can also have differences between what the robot believes and what the robot believes the human believes, of course. This is the main operational cycle of the GSM. And again, we also have the possibility of going from situations to histories. So there's a history type that contains moments and events. Moments are situations. For the case of events, we have event classifiers. Events are basically significant changes across situations that might or might not have duration. So in total, we have two types of classifiers. Categorical classifiers, going from the stochastic layer to the categorical, and basically dealing with the meaning of adjectives. And event classifiers, which basically deal with the meaning of second person or third person verbs, as we're going to see. So in total, if you want to have a view of where the semantics of verbs and adjectives are within the GSM proposal, the most crucial point for adjective meaning is the categorical classifiers. And when it comes to the verb meaning, the second and third person verb meaning is basically encoded within the event classifier. And the first person sort of verb meaning is encoded within the action controllers. Let's have a look at the video example again now.
Where is the red one?
At the top.
Look at the center.
Okay.
So this is a depiction of the continuous layer. It's the most likely state of the situation. But we're keeping many alternatives too. This is a stochastic layer for position and the stochastic layer for size. And this is a camera input. We're not viewing the red object anymore, so slowly its position distribution diffuses.
Where is the red one?
Most probably at the top.
What color are the objects?
One is red and the other is green.
Imagine a blue object on the left.
Okay.
Now notice that because we haven't seen the red for a while, its position distribution has spread quite a lot. When we heard the imagine statement, we just feed the categorical layer through the stochastic layer, and we get the receptive region of the classifier for left, filled up with the probability mass, so it might be anywhere within here. And also, because we have no information about size, again, we get a uniform distribution on the categorical, and we get the receptive region for all three categories, actually, for size.
Where is the blue one?
Most probably at the left.
It has went out a little bit.
How big is the blue one?
I have no idea.
Look at the left.
Now the matching algorithm is going to take over.
Okay.
And the expectation that we had gets matched with the sensory evidence, and we update the information so we get a better estimate of the position and the size.
How big is the blue one?
Small.
How big was the blue one when your head started moving?
I have no idea.
Now we go back in time, we resolve the event description, went back in time and answered the question.
Where was the red one when the green one appeared?
Again, when the green one appeared.
Most probably at the top, but maybe not.
Thank you.
You're welcome.
Good. So let's have a very quick view at the modular implementation architecture. This is how the system breaks down to sort of software modules that communicate with each other through PVM. At the center, there is this sort of situation model database, which keeps the current situation. And this is being sent over to the modality-specific instantiation module. So this is a module that proposes changes to the situation on the basis of visual evidence, one for proprioceptive evidence, and one for linguistic evidence. Here we have sort of the sensory chains. Down here we have this episodic memory. This is sort of the action controller for both speech acts and motor acts. Now let's go to the implemented system. So this is a generic proposal so far. If one wants to build a system out of it, he has to get basically choose an embodiment, which provides some constraints, get a behavioral specification, and then on the basis of that, customize the generic GSM proposal and build around it in order to get the implemented system. And there's also a simple design methodology within the thesis. So this is the embodiment that we were given. I talked to you about it before. Microphone, speakers, cameras, joint angle encoders, grippers, 7 degrees of freedom, and so on. This was the behavioral specification that was set. It includes a couple of new things that you're going to see now in the next videos, apart from what you saw before, including actually multilinguality, basic multilinguality. This is a customized GSM, which also have 3 agents, one for the robot, one for the human, one for the objects. These 6 types of properties, these event types, and we coded event classifiers for them. And we had specific sensory connections between these properties and sensory elements. So for example, the position of the human agent is connected through a visual evidence from the face detector, and so on. The vision system has 3 main chains, one for detecting objects on the table, the other for detecting human skin, which corresponds to hands, the third for detecting faces. When it comes to spoken language processing, there's a part that deals with understanding and a part that deals with generation. Generation is pretty simple. It's based on decision trees and templates. So when it comes to generation, because the language that we have is pretty simple, we can do keyword-based semantic frames and just extract a couple of significant features. Basically, we do sort of a bag of word spotting, and we impose the syntax through a trick. There are fixed routines for object-referred resolution and temporal-referred resolution. So here the question is how to go from object description to finding out the matching objects. Here's how you go from event description to finding out the matching events. Verbalizing uncertainty gradation. So in case I have less certainty about a thing, what should I say? For example, I will say red, most probably red, either red or blue, or so on. We use this decision tree. This, again, in principle, could be empirically trained. Going from referent resolution to action execution. So say that I say to the robot to give me, the red one, and there are 2 red objects. What should it do? So in this case, for example, it goes down and says, you mean this one or that one. In the case where I have singular or plural, different things happen, and so on. Now, some of the extensions that you haven't seen before. Watching human hands. And trying to do human hand event detection. So why is this important? Why do we deal with this thing? Notice that the robot has the capability of performing some motor actions. So it can actually, touch objects, pick up objects, hand objects to humans, and so on. Ideally, we would like for a robot to be able to recognize the respective actions when they're actually being performed by humans too. And this is extremely important in order to get a more sort of symmetrical relationship between the human and the robot, because by recognizing them, you can actually do learning tasks through imitation, through visual-based imitation. You can also basically try to start to coordinate your actions. In order to be able to collaborate with the human, you need to know what the human is doing at the moment. So it's one of the extensions towards action coordination. Then we try to move away from simple blob models for objects and to go to voxelite shape models. We did some experiments on multiple view reconstruction. So we get this modulated cones, basically, and through the intersection of the modulated cones, you can slowly converge to the right shape of the object. And then you can get this into the categorical layer, go to verbal categories. So this is the actual voxelized model of the puck. You're going to see it a little better from here. And so on. This is the current behavioral repertoire of the robot in terms of almost a context-free grammar. Another thing to notice is that we have this simple multilingual extension for English and Greek, but you can actually do Greek only through the console because we don't have speech recognition and synthesis. And this extension gives us another interesting capability, which is the capability of using the GSM as an interlingua for simple translation. So when we get to the point where we can do full story understanding, so instead of statements about the current situation, when we get to the point where we can actually describe histories of events, then one can basically describe a history in English and then query the whole episode in Greek. And in this sense, we're, in essence, basically doing rudimentary translation by using the GSM as an interlingua. Of course, right now it's a very, very simple level. It's just an indication of things. Evaluation. We have novelties for the system and qualitative evaluation. We have some generics about evaluating such systems, quantitative evaluation in comparison with a token test. There are three novelties above the state of the art as represented by these systems down here. The capability to imagine situations and deal with informed speech acts, the capability to remember and resolve temporal reference, and quantifying and expressing confidence. We propose a set of different levels for evaluation of situated conversational assistants. And I think this is quite an interesting proposal. There are many ways to evaluate such systems, and this is sort of a hierarchy of ways. So it's pretty much similar to actually testing humans that are performing something. You can either go and test at the module level and have a look at how good the vision system is or speech recognition is. You can go to the system level and deal with interactions of multiple modules. For example, try to find the transfer function between external reality and the internal situation model, how much delay there is, what errors and noise there is. You can go at the task level and talk about performance for a given task. You can go to the user satisfaction level, pretty much like dialogue systems, and see how satisfied the user is when he interacts with the system. And you can go all the way to the human replacement test, where the goal is to replicate as closely as possible a human's responses for the similar situation. And there's also a whole sort of part of the thesis talking about how one can use human psychological tests as either design specifications or evaluation methods for SCAs, and what are guidelines in order to use them in a meaningful way and not to cheat, and so on. Now the quantitative evaluation. This is a task-level evaluation. There was a task of 10 turns with a rich mix of commands. The human was instructed to repeat the command if it was unsuccessful. There are 4 different types of errors, possible types. There were actually only 2 of them were exhibited in these tasks. Speech recognition errors, vision system errors, mechanical manipulation errors, and category misclassification errors. These are actually quite interesting. This is a case where you refer to an object's property category and the robot believes it has a different category. So this ball over here is green, but it's a little marginally green. Different lighting conditions, the object very often thinks it's blue. The robot very often thinks it's blue. So there is a case where you actually say, touch the green one, and instead of that you get a response that no such object exists. But through small, again, changes in lighting, because this is sort of a borderline case, you can go back to thinking that it is green. There can be other category misclassification errors regarding size or position or so on. Also notice that there are 2 types of errors in terms of how catastrophic they are, actually 3 types. There are errors that you can repair by repeating the command, and there are errors that are going to destroy the execution of the task. So let's have a look at one of the trials.
Look at the table.
Okay.
Where is the object?
This is one of the worst, actually, trials. There are 3 consecutive errors and very funny.
How big is the object?
Small.
Touch the green one.
No such object exists.
So touch the green one, no such object exists, because the robot is actually thinking it's blue right now.
Touch the green one.
What about it? Ask again.
Touch
No
the
such
green
object
one.
exists.
So that's a little more complicated. The human says, touch the green one again. The robot hears 2 things. It hears what, and then it hears touch the green one again. He responds for the first thing, what, which is a speech recognition error, by saying, what about it, ask again. And then again, you get 1 more categorical misclassification error. And finally, with the third touch the green one, he has actually changed his opinions about the categories, and he thinks it's blue, it's indeed green, and he accepts it.
Okay.
So this was a non-catastrophic sequence of errors. We can actually continue with the task and be able to go all the way through it. If, for example, the task included an imagined statement and we imagine something different than what we should, then it would be a catastrophic sequence. We would never be able to recover the right answers for the rest of the part. Or if, we slipped an object or something like that.
Imagine a red object at the left.
Okay.
How big is the red one?
I have no idea.
Look at the red object.
And everything goes well for the rest of the task.
Okay.
How big is the red one?
Small.
How big was the red one when your head started moving?
I have no idea.
Where are the objects?
One is at the center, and the other is at the left.
Okay. So what are the results? First of all, error analysis. 87.1 correct responses to human utterances, 8% speech recognition errors, and 5% category misclassification errors. I must admit over here that the speech recognition errors are actually pretty good. They can be pretty good when you have a native speaker. When you have a non-native speaker, because we're not retraining the speech recognition, they can be pretty bad. And of course, the noise level plays a very big role in that. The most vulnerable turn in the evaluation was the turn that you actually saw the mistakes happening, touch the green one, because there you can have a probability of both SREs and CMEs. Now, the good thing was that all tasks completed successfully, but there were repetitions in order to do that. The median extra task length was 1 utterance, 1 repetition. The average task prolongation was on the order of 11%, and there was an average of 1.18 errors per task. The timing is pretty natural for the type of task. We have 78 seconds for the 11 on average turns, 10 plus a repetition, and 6 seconds for each turn duration. So the system is not infallible. There are these types of errors, and in other cases also others. But we get task completion after some repetitions, on average 1 repetition per task, which is not so bad. It works. Now, module level evaluation. Here we just isolate specific modules. For example, we talk about motor control capabilities. We got 100% performance for touch, which is pretty simple to do. It's difficult to miss it. Hand-me, there's a possibility of gripper slippage. And now when it comes to category misclassification errors, red is pretty stable, but for the green ball that we had all of these problems with thinking it's blue and so on. We can retrain the categories, of course, for that. Now let's go to human replacement evaluations. There is a token test for children that was created in 1960, I think, somewhere around 60 in Milan, as a test for aphasics originally. And later in the 70s, it was used as a test for 3 to 7-year-old children. And these tests are pretty useful as evaluations and behavioral specifications too for robots. So you have a set of tokens, and there's a test giver and a test taker, and the test giver gives a number of commands, and the test taker is supposed to respond correctly. Things like touch the small blue square and the small yellow circle, put the green square away from the yellow square, and so on. This is a comparison of the current capabilities of replay as compared to the first 4 parts of the token test. And in general, as you can see, in some respects, we're actually surpassing the requirements. In others, we have a small misalignment. I think the general result from all this is that we're pretty much at the level of the first 4 parts of the token test, plus we have some things that are not even assessed over there at all, like informed statements, remembering, and so on. Future extensions, there's a huge discussion of future extensions, a plan of 5 or 10 years in the thesis. These are roughly classified across 3 domains: the sensory domain, the cognitive and affective domain, and the real-world operation and design. And the main thing to notice is that these are not separate projects. These directly build upon what we have, and if we didn't have what we have, we would need much more time in order to get there. I will not get into details. Now, discussion in relation to AI, semantics, and philosophy. There are all of these different sort of blocks of discussions. Let me go through some of them. There's a whole discussion of meaning spaces. What are possible meaning spaces to ground out the meaning of words? Also, sort of a small plan for grounding out the whole language. There's this discussion of semantics of verbs and adjectives within the GSM proposal. There's a discussion of successive approximations of meaning models. So right now we have pretty absolute meaning classifiers. So for example, small means something that has radius less than 3 centimeters or apparent radius. How do we get to sort of noun-specific